Okay, so then the aim for today for the session is really to solve and to work on and to calculate on this first example that we introduced last time about this company that makes investments and gets some return and tries to make optimal decisions, which was a little bit, we will go over the example in a second. It was a little bit weird, but is really, I think, a really good tutorial example. And yeah, so what we will do is first the deterministic, I have to say here, deterministic Markov decision process example. This will be the just rehearsing what we basically did last time, and then application of the Bellman equation system. Did we see Bellman equations last time? No, we didn't really get up to that, right? Then I have to introduce that as well. Then actually, I thought this is what I forgot. So we first go over the example again, and then I will introduce the Bellman equations, and then apply to example. And this will really need some computing or calculations. So, okay, then let's go. So the way I formulated a Markov decision process as a model for some real-world problem, this is how you always need to see that. So there's a real-world problem that you somehow want to address in a computational manner or in a modeling manner. So you formulate a model of it, and one model class obviously are Markov decision processes, and we here look at what I call deterministic Markov decision process because no probability was involved, and I formulated this as this tuple T S A R. And then I include the variables because usually they are not included, but I feel like it makes things more explicit if they are included. And then there are these two functions. So that was what I termed a deterministic Markov decision process. And of course, now that this is 1 week ago, and you didn't have the material only in German. And actually, in this German material, which I should cite again here, Schild 2017, this formulation in terms of a deterministic Markov decision process is actually not in there. So it does it without the formulation of the model. So let's go again over the components of this model. So T was the number of decision epochs, so number of decision epochs on this investment epochs for the company. So that's a number, for example, 10, and we will later see it for 3. S was what is called state space, and that is usually just a set of numbers. Can also be, of course, a vector space. And for the company, these were the possible capital stock values. Yeah, capital stock values. So these are the values that the state variables can take on. So we will see in a second. A was the action space, and for the company, this was the possible investment. Then we had the reward space. Which was the possible net capital stocks. which will be clear once we look at the reward function. Possible net capital stocks. And then, so I will do that briefly now. So these are the capital stock or state variables. These are the action or investment variables. And these are the reward or net capital stock variables. So that's essentially the same as the state space, but of course the spaces, the state space, the action space, and the reward space. But of course, these are the state space, the action space, and the reward space are sets of numbers, and these variables are variables that can take on specific numbers. And then the important or the most important thing that gives the whole thing its functional properties are, of course, the transition and the reward function, and F was the transition function, state transition function. So, state transition function, and for the company, that was this function that determined the capital stock at decision epoch t+1 as a function of the state and the action at time t. And this was given by st plus at. Yeah, that was this idea that the company has a given stock, it can make an investment, and this will lead to a capital stock of the capital stock at time t plus all of the investment at the next time point or decision epoch. And G was the reward function, which for each time point yields a reward, or in this case a net capital stock. And there the idea was that the reward at decision epoch t is dependent on the state and the action, so the capital stock and the investment, and is given by st minus a square t. So the investment actually is costly to the square, but then of course if you make a high investment, then you also get the output at the later state. And then, so that was what we referred to as, or what I refer to as the process. And then we discussed also the problem, which then was to maximize the cumulative sum of rewards, which of course here is given by st, we don't need these brackets, st minus r square over all time points and with respect to the actions. So the actions, which are all these investments. And then we discussed briefly that so one can write the problem fully as subject to the transition. So essentially one writes up the functional properties again, st plus at and s0 norm. So that was then, that is then the problem. So that's the problem to maximize this, given the scenario that was discussed. And then I think we discussed the notion of policies and the decision rules and policies. So then we talked that what we're actually interested in are decision rules, which are functions of the state or the capital stock and yield an action. So the idea is that a company has a given capital stock at time point 3. What is the action that it should take? and that's what a decision rule then answers. So it returns for each state, so in principle state dependent, an action, not necessarily an optimal action. This is just a decision rule. Same for the policy, which is just a sequence of decision rules. So a sequence of functions from 0 to t. And then I said something that this is really complex because you have you are looking for an optimal set of function that maximizes the cumulative reward. Yeah, there's the tilde. Yeah, and then I think I introduced the yeah, okay, and then we did the optimal value functions. Value functions, which now that I did this, or like this, which were defined as VT, ST, max AT to T. So the difference in terms of the general problem was that these now start only from T on. So the sum runs from T to big T. That's a typo. G, S, K, A, K. And this, of course, subject to the same constraints. So subject to S, maybe I put it there. Subject to ST plus 1 equals ST, sorry, F, ST, AT, and ST, yeah, equals, this is why I had this tilde, but one, and we can also put ST known. One doesn't need the tilde. So these optimal value functions, they were just introduced without really more as a definition than discussing what they are useful for, because they are useful in the Bellman equations, which we hadn't discussed. Yeah, so that was roughly where we went up to. So that's already quite a lot, as you see. So we have defined a model for a real-world problem for this company who does investments and gets stuff back. The important things, the most important things being, of course, these functions. We have the problem of maximizing the cumulative reward without any discounting or so, which one can also do, but we are not doing. And we have a little bit towards the answers. So we want to find decision rules and policies that actually maximize this. So we want the optimal action for each time point, and we want an overall decision rule that gives us that. And one thing that we need is the optimal value function. Yeah? So that was kind of where we went up to. Now, the solution, so this is all more the problem. So the solution is actually given by what is known as the Bellman equations, aka the dynamic programming algorithm. And maybe before I write them down, these solutions are very much alike to what you know from school and how to maximize a function. So if you think of, you have a function fx minus x squared, then you know, and you learned in school, that you can find the maximum of this function. So this function looks like this. Oops, actually, of course, goes through 0. Roughly like this, that you can find the maximum of this function by computing the first derivative, setting to 0 and solving, and checking the second derivative. Yeah, so this is how you maximize the function in school. I assume everyone did that. So where you determine critical points, so maxima, minima, and saddle points. And the same kind of answers is actually the same kind of logic is what the Bellman equations give you. So they don't, they give kind of an implicit and necessary, necessary and sufficient conditions for optimal policies, but they are more like a general rule how to address such a problem. Like your math teacher in school said, to find the maximum or to check whether there's a maximum, you have to compute the derivative and then solve. That doesn't tell you how to do that exactly for a given function, but it gives you a general principle. And this is exactly what the Bellman equations and the dynamic programming algorithm do. So they give you the principle, but then you have to work. Same with variational base. So that's also just the principle, and then you have to do the work. So then let's now finally, after so much hype about them, but no delivery, let's talk about Bellman equations as necessary and sufficient conditions for optimal policies. And I will just write them down, tell a little bit about it, but then you will only really understand, and I don't know, maybe you understand them without. I only really understand these solutions if one actually applies them in an example, and then we want to apply them, of course, to the company example. But this is not really the kind of solution theory, and so here I'm trying to be very close to the Schild stuff, because I don't want to get it mathematically wrong. So Bellman equation, that's actually something to discuss in a second. Bellman equations as necessary and sufficient conditions for optimal policies. So of course this whole thing unfolds now on the background of a deterministic Markov decision process that is formulated. So you need to define what we defined above, and then the following is true, and as I said, we don't prove it. If the optimal value functions exist, if the optimal value functions exist, which is already kind of a deep mathematical question, but here it means if for each optimal value function for t, for each state that can be the argument of that function, this value is well defined, so it's not infinity for all t, and we will, of course, we will not care about this, so we will not try to show that for our example this is actually the case. But mathematically this is, of course, something to do. Then every optimal Markov policy, actually Markov in the sense that it's only dependent on the current state, policy pi star. So the star is for optimal, and as you remember, a policy comprises decision functions, and an optimal policy, of course, only consists of optimal decision functions. Of course, this is with respect to an optimization problem of the problem. Just to make this full, of the problem max over a0 to t, at, and a, the cumulative reward function. And this is why I like to first define a Markov decision process, because without defining that, you have so many things here, and you get lost. Might even get lost this way. Subject to st plus 1 equals f st at s0 known. So if the actual value functions exist, so if the then every of the problem, this is the problem, satisfies, and now we get somewhere, satisfies that the optimal decision policy, the optimal decision function at the last time point st for the value st is the maximizing argument of g st at. So let me first write this and the other one, and then I explain what this means. So that's for the last one, and for the other ones, it's similar but more intricate. This is actually what Google DeepMind does, if you're interested in that. So it's not some random stuff that I'm doing here. Plus vt plus 1 f st at, and this holds for t minus 1, t minus 2 to 0. So what does this first mean? We will have to talk about, there's a little bit more, but let's first talk about this. So the thing, what this says is essentially if the problem is somehow okayish, so if the optimal value function exists, but we don't care about this, so this is mathematical subtlety, then the optimal decision functions fulfill the conditions. And the way you have to think about it is that this st is, of course, a value in the state space. So it can take on all values in the state space, essentially. And the decision function was a function that maps a state variable onto an action. And the action that is thought for here, that's the optimal action. So you're looking for the argument that maximizes the final reward function. So what here on the right hand side, so this argmax g st at, if you this means you are maximizing over actions, and what you return is an action. Yeah, so you get out. You can also write this here as the optimal action at time point t. And to find that, you have to find the maximum of the reward function at the final time point with respect to the action as a function of the state. Yeah. So the state remains a function because you want the optimal decision rule for all states, so that it remains a function of the state, but you maximize out essentially the action at the last decision state. Yeah, so you get the optimal action as a function of the state at the last point. That's for the last one. And then all other all other optimal decision functions you get recursively by finding the maximum of your reward function at this time instance, plus the value of the optimal optimal value function at the location of the next state. So one way to say that, but this also doesn't make it clear. I think it only gets clear if one actually does the calculations. But one way to say that is that you assume that you behave optimal after the current time point, and from this you derive it. But this is something one can say, but I think one really has to see what this means in action, so to really get what's going on. But what also here is the thing is that you maximize the whole thing over action, so that the thing just still becomes a function of the state, because you want to know at each time point, whatever state you're in, what is the best thing to do. Maybe I go on a little bit, because what we haven't seen yet, and why it's really quite hard to evaluate this, is because the only thing because these value functions, although they are defined, it's also not clear what kind of values they actually take on. And this is what the Bellman equations actually yield. So, and the optimal value functions. So we just gave our abstract representations, but we didn't know how to calculate that for our example. And the optimal value functions Vt satisfy the Bellman equation and usually it's referred to as Bellman equation. I will call it here Bellman equations because, as you will see, these are many. Vt, so at the last time point, this is the maximum over actions of the reward function. So it's very important that you note the difference between argmax and max. The argmax gives you the argument that maximizes the function. So in this case, because you're maximizing with respect to actions, it gives you an action. The max gives you a value of the function at the location of the optimal action in this case. So here you get a value actually of the reward function evaluated at st and the optimal action. So that's different. So the value function gets values from the reward function. And for all remaining points, it gets very similar to the above, g st at plus vt plus 1 at the location f st at for t by t minus 1 to 0. So one last thing. So this is the necessary not last thing. This is the necessary condition. So that's like if there is a maximum at the location x star, then the first derivative is 0. So this is like if the maximum then the optimal value function satisfies the optimal value functions and the optimal policy satisfy these conditions. Now the other way around, in the sufficient sense, if functions Vt exists for which the Bellman equations hold, and these optimal functions here define a a Markov policy, so that means that they only depend on the current state. Define Markov policy. Then and this P is a solution. Oops, as a solution of the problem and with this problem star I mean this problem. So I appreciate that it's really not really understandable if one doesn't do an example, which we will do in a second. The thing is, it's a different way to say, like your math teacher said, to find the maximum of this function, you have to compute the derivative and set to 0 and then solve. And then check the second derivative. And this says, if you have this deterministic Markov decision problem, what you have to do is to calculate, you just basically have to calculate these things that are stated here, and then, given some mathematical subtleties aside, then you have the optimal policy. But you still have to calculate it. It doesn't come for free, and you have to calculate it in a given example. This does not solve the problem. Why? So this is not what the Bellman equations answer if you don't prove them. So, like in math, if they told you you have to compute the derivative and set to 0, then of course you can ask why. And that would be a proof of showing that this procedure actually works. And of course the Bellman equations and this algorithm that becomes dynamic programming if you do this starting from the last time point and going backwards in time, this is not justified here. Yeah? And there are, of course, proofs. So, Zane, you looked into the proofs. I know because we looked at them, because they are in books, in for example, the Bertika's book. But I also have to say the proofs that I've seen, you essentially have to do things that you exchange maximization and computing expectations if you're in the probabilistic case and so on. And so I haven't seen in the Bertika's there's one easy proof, but then the easy proof you ask yourself, do I really believe that? And then you let down further and further down in the mathematical road, which is interesting. But even if you understand the proof, you still don't know how to actually apply this in a given example. For example, if you're doing decision neuroscience and you have your favorite new task and it's relatively simple and you ask yourself, so what should the person here do? And do humans actually behave roughly as they would do if they are doing it optimally, because the brain is wired in such a way that it somehow can integrate all this probabilistic information and do things correctly? Or is it not? Are humans not rational? So they behave completely different. Or what are they doing? Can we approximate the optimal solution roughly by some heuristic and so on? If you have these questions, then of course you have to apply this for your task. And then it doesn't help you if you know the proof. It might help a little bit, but in general, it's something different from proving that this solution that I just wrote down here works from actually applying the solution. So the next thing that I really want to do is then apply the solution, and hopefully by this make it much more clear what's actually going on here. So, questions right now. Do you need a break? I don't need a break. I haven't really started yet. Yeah. Roughly the same. The difference that comes in is that you get an expectation operator, because things will become probabilistic here. So the transition gets probabilistic, and you have to compute the expected value of the optimal value function. So that makes it more complex, because you always also have to keep track of with respect to which probability distribution you're actually currently computing the expectation, which is often in the notation that is used not really clear. But that's the main difference. So that the algorithm looks roughly the same, but there's an additional thing that you have to compute expectations. And if you actually have to do that, then you need to know with respect to what. But otherwise it looks the same. This is also why I think it's helpful to go over this, because then then one sees the general mechanics of the algorithm, and then making the step to the probabilistic is just integrating into the whole procedure now the idea of computing this expectation and keeping note of which probability distributions are involved, but one has an idea of the general mechanics. So that's why I like that. Okay, other questions? No. Yeah.
What's the meaning of distinguishing decision rules separate from actions? Because they eventually become something.
Yeah, that's a good point. So let's briefly rehearse that. So what I mean by a decision rule is a function that takes in a state and returns an action, and an optimal decision rule, which we are now interested in, of course, returns an optimal action. So this takes, for example, this takes the state as t and returns the optimal value of the optimal value of the decision rule for state as t, which is of course the optimal action. Have a look at this. So sometimes you see it written like this, but no, yeah, this is what I'm trying to avoid here, and this is why I do extra care to dissociate decision rules from actions, because decision rules are functions that for each state return an action. And an action is still an action, and of course the decision rule tells you, okay, the state is now that, which action should I take? And if it's an optimal decision rule, this is the optimal action. But this is a so the decision rule is a function, and the action is just a value in your action space. So I don't know if you know Lilla's treasure hunt thing, then the decision rule would be you're currently at a given location and you see these kind of light bars, which action to take. So that's the rule. And the action would then be to go northwest, south, or anywhere. Yeah. So, and these are two different things. One is the rule and the other one is the value that you actually take. Yeah. Good. Yep.
Is Google DeepMind is using one of those functions, so they try to program their AIs.
Yeah, exactly. That's so what they are doing. So they so what is coming together in at Google DeepMind, although it's. I just said that to make it also a little bit interesting for everyone. They don't. The problem is that Google DeepMind, they don't tell you really what they do. Is what I find. So whenever I look at it, I don't get really what they're doing, because they're a company and they don't want to tell you exactly what they're doing. But there are three founders, I think. One is Demis Hassabis, but another one, he has done a PhD thesis, and I think some of this theory is going into that, that is essentially based on dynamic programming. It's a specific way to do these recursive evaluations to solve these optimization problems. This thing is, this might look like a specific solutions. Often it's not really clear how to compute these things. And in the simple example that I showed you, one can compute it. But in more real life problems like Go, which is not really a real life problem, but it's, or card games, which is also not really a real problem, it gets much more complex, and then there are different ways to compute these things. And this one guy in Google DeepMind, he has a strong background in dynamic programming and a specific way of doing these recursive evaluations. And what they are also doing is, I think, although I'm also not quite sure, is that these value functions for real problems, they become really hard to actually compute, to know what the value functions are. And they have some, so they use some deep learning stuff to approximate these value functions. There's a book by Bertzikas from, I think it's 1999 or so, that is called Neurodynamic Programming, which for complex problems also goes into how you can use neural networks to approximate these value functions. And this is kind of, that's kind of the technical background that Google DeepMind works on. Yeah, because it's a typical AI problem. So you have some, I mean, you can, of course, also program robots based on this. Is always the question. So you have a goal, and somehow you need to find how to achieve that goal, and then you try to find an algorithm that does that. Yeah, but yeah, it's a hot topic, although it might look fairly boring. Other questions? No. Good. Good. Then let's really see what this now means, because that might make things a little bit clearer. And the only thing that you need actually to understand what we are going to do next is that you remember essentially how to maximize a function like, let's switch to black again, how to maximize a function like you've seen in school. So again, something like x squared. Then you know you can compute the first derivative. For example, in this case, you need to take the 2 down and subtract 1. So these are little things that you've done in school. Maybe you forgot them, but you knew them at one point. And then you know that you can set the first derivative to 0 and solve for x, and in this case you divide by -2, so you get x star, so the optimal is at 0, which you already seen from what I've drawn here. So this is 0. And then you can also compute the second derivative, which here you get then x to the power of 0, which is 1, so you get -2. And then you know if the second derivative is negative, then it's a maximum. If the second derivative is positive, then it's a minimum, so it switches around there. Can those people from the bachelor raise their hand if they have seen what I've just described? Have you seen that in school? About 10 years ago, and you have forgotten all about it, but that's something that one does in school, actually. Yeah. Because good. And this kind of thing we actually need now. Otherwise, this is the whole thing with the whole dynamic programming. The mathematics, especially in the discrete case, the mathematics is not advanced. The problem is that it's so much notation and so many individual components that make this a little bit like, wow, what's going on? But the real mathematics in the discrete case is not, it's in the end, it's high school math. It's just with a lot of indices and a lot of variables and so on, but that's about it. But it's enough. I mean, it's really something to struggle with. Good. So now how to apply this in our example. So in our example, we had defined these things. So we had our RT, so our reward function defined as this, and we had our transition function defined as this. And now the Bellman Equation dynamic programming algorithm says to find the optimal decision policy, the optimal decision rules, which we then can put together to an optimal decision policy, says we should start by computing this here. And then once we have this, we can use together with this here. So we have to compute the optimal decision policy and the value of the optimal value function. Then we can use this to compute, then we have this actually, we have this, then we can use that here. And then we can compute the next optimal decision function. So what it says as an algorithm is that we should start at time point big T, so at the last time point, put in our reward function and do these maximizations. And then we should compute all the way back to time point 0, so that we then know what's, that we then have it for all time points T. Yeah. So that's the general algorithm. So start from the last time point and work your way to the first. Or
Can you quickly say, so the VT plus 1 in the second equation for the T's, not the capital T. So I understand that this is the value function from the trial T plus 1, but at capital T, we don't have anything like that. Of course, we don't have a time point behind our final time point, but this is then just 1 or?
No, it's this. So this is at big T.
Right. So this is actually.
This is just the reward. That's the final reward. And we actually have to also start there. And then when we want to compute this for T minus 1, we have V capital T. So we have this. Yeah. But we will see that now.
That's just any real number. That's the reward in the last two.
Yeah, I mean, it's this. So let's do it in an example, because then I think it gets clearer. But what I wanted to say is that we now compute this. So we apply to our example, apply dynamic programming, deterministic dynamic programming to our example. And in the example, we can actually do that manually. In real life, for more complex things, of course, you would use a computer, but we will deal with it actually analytically. So then you would actually, for computing, need some symbolic computing or something. So, yeah. So the general outline is we start at the last point and work our way backwards. Yeah. So we start at time point T equals big T. And we will actually compute this for T big T, then T minus 1, T minus 2, T minus 3 maybe, and then stop and then see, oh, there's a general rule that we can prove by induction. In real life problems, you might, if you apply that on a computer and your T is okayish, then you might actually do that explicitly for all steps. But also in kind of the analytical treatment, the dynamic programming algorithm gives you a way to do analytic solutions. Yeah? And this is what we focus a little bit more on here. But it gives you both. It gives you the possibility to evaluate that numerically and analytically. And we're going a little bit down the analytical route to see really what's going on. And yeah, if you look into the Markov decision process books, that's what they usually discuss. So it's usually a good idea to find the general optimal policy to compute that explicitly for a couple of steps and then use a structural approach to prove that you found something. So, viel Vorrede, now let's do something. So, Vt, the optimal value function, is, according to the Bellman equation, given by the maximum over AT in A of the reward function at the last time point. So I'm using this right now. This is what this says, and we need to compute that to I mean, we get two things. If we find the maximum, then we of course also get the maximum action. We also get this. We also get the argmax, and we need it for the next time step. And this is, in our case, max over AT in A max ST minus A square T. This is just the definition of our reward function for the case of the company. Yeah? Do you remember that? I don't have to scroll upstairs. This is just the reward function. Now, what this says is that we should find the maximum of this function here with respect to AT, and ST remains a variable. Yeah? So to make this really simple, I mean, some of you might have an idea. So maybe let's ask, so does anyone have an idea how to find the maximum of this function here now with respect to AT? We just discussed it, but maybe say it.
For every action. Compute it for every action.
No, you need to find the maximum of this function.
Oh, you mean the derivative and these ideas.
Yeah. So what would you do? Yeah, but what? So what would you do first?
First derivative.
Compute the first derivative. Yeah, and then?
Then Nullsetzen.
Yeah.
And then second derivative.
Yeah, exactly. Good. And one can. So the way I'm doing it here is that I'm. But this is just for me to be really clear. I define a new function. Just to get this really into the context of what we need to do, I define a new function h, which I define just as st minus a square t. And the aim is, this is of course just this thing, the aim is to find the maximum of this function with respect to a. And then, as discussed, we have to compute the first derivative. This is a function of at, so that means that st is a constant. So what's the derivative then? Minus 2at, exactly. So this is a constant. This is something like 3, for example. And if you compute the derivative, it goes away. And here you just do, like, you have a square, so you have a polynomial term. So you just take the number that is in the exponent before it and subtract 1, and then you get this. While we're at it, we can also compute the second derivative, which is what? Minus 2. And then we can use this to actually compute the optimal action set to 0, which then says minus 2at equals 0, which then of course says at is 0, because we just divide by minus 2. And this is now our optimal action. And what we are actually looking for is the value in this case. We are looking for the value that this function takes on at the optimal action. So what's that value? So if we, maybe I write it up what I'm looking for here. So if we and this is just about basically notation. We have now done the optimization. We have seen where the function takes on its optimum, and we have found what we can call the optimal action. We can also call that the value of the optimal decision function. Where's the square? There. St minus the optimal action. And what is that? St, exactly. So.
Wait. Question.
Yeah.
A star big T means the optimal action at the last time point.
Exactly.
But if this is an invest problem, and then why would you invest in the last time point?
Yeah, this is the question is where. No, well, because the reward function is defined like that. So, like I said, the problem is not the greatest problem specification ever. So you could also say, yeah, we don't invest in the last action anymore. But then the reason why it turns out like that is that and also the example is time invariant. So the reward function is always the same. And you can also define a final reward function that is only dependent on the state and get rid of the action there. So one can do these things, and to make things more lifelike, of course, one can build them in, but for simplicity, we have this arbitrary thing that they invest at the last time point, although they will not get at and afterwards they will not get anything. So it's just mathematical simplicity really here.
But equivalently, you could say, because of the way the problem is defined, in this case, the invest company problem, then you can already say that A star big T is equal to.
No, I wouldn't say that. So another option would be that you define a reward function for the last time point, in addition to the reward function that you define for every other time point, and you define that at St. And you don't make it a function of action anymore. This is one way one could do it, but then of course you would have so the whole thing here, and this is how general Markov decision process are of course defined, is that these things are also time dependent. But I did not do that here, because then you say, okay, this is everything time dependent, then in your example it's actually not. So that's, so I think we clarified that. So let's go back here. So now there are, the thing is, what did we learn? And I'm writing that up for the last time point again. So the optimal decision rule, which is a function from states to actions, takes the final state, maps it onto the optimal action, which is the same thing as the value, of course, of the decision rule for the state, and this is 0. So you see that actually here this is not dependent on state, so it's a constant, but in principle it's dependent on the state. Yeah, just in this case it's not dependent on the state. And the optimal value function is what we've just seen above. So the optimal value function, which maybe I write it here as well, is a function of the states and returns a number, takes a state, maps it onto the value of the optimal value function, and this is in this case actually St. And this is clearly dependent on St. Yeah, this is St. So what we actually computed now in terms of Bellman is this and this. Yeah. Now we want to compute the stuff for t minus 1, and if we are at big T minus 1, then of course this thing here, v t plus 1, is Vt, and we just computed that. Yeah. So now we're now also in an algorithm, so we're going to the next iteration. So we are going to t minus 1, and here the Bellman equation says, if we write it up, just now plugging in t minus 1 for the big T, it says the value of the optimal value function at S big T is the maximum over a t minus 1, our reward function at S t minus 1, a t minus 1, plus the optimal value function Vt, which we have here, evaluated at the transition function in turn, which is evaluated at a t minus 1, big T minus 1, and st minus 1. Yeah. And again, this is something we now have to compute, and of course we need to substitute things there. So what does this really mean? So our reward function is always the same. That's always st minus a t minus 1. So just again, here I just wrote up this thing for t minus 1. Yeah, I haven't done anything else. I just plugged in for the small t that you see here. I plugged in t minus 1, and now I replaced the this one by the reward function already. And now I think the only tricky thing happens. We have to think about the optimal value function v big T at the value of the transition function evaluated for st minus 1 a t minus 1. Oh, sorry, square. Yeah, thank you. I forgot something here. That's the square, which of course we can also look up. Scrolling through the whole thing, which we can look up here. And we also need this. Now we need the transition function. So let's plug that in downstairs again. Are you getting dizzy because of the scrolling? I don't know. Vt at st minus 1 plus at minus 1. Now we have to think a little bit about what does this make sense, and yes, it makes sense. So think about the transition function. It takes in a state and an action and returns a state. The state that it returns is of course st plus 1, which is of course st. And this state st, so if whatever goes in here, is just given by the identity. So to make this really concrete, what this means is, for example, if st minus 1 is 2 and at minus 1 is 1, then this says compute st minus 1 plus at minus 1, which in this case is 3, and plug this into the optimal value function at the final time point. So put this in here, and then if you evaluate this, you get 3. Yeah. Now, if we do that in more abstract terms, what we get is st minus 1 minus a square t minus 1 plus st minus 1 plus at minus 1, because these two together are st. Yeah. This is what confused me a little bit, but then I think I now got clear, because if you think about what's happening, it makes sense, because this is just st and this function returns st, so it needs to be there. But then we actually have our problem of what to do for a big T minus 1 written up much easier. So we need to now maximize this function here again with respect to, in this case, a T minus 1. To ease that, what I find helpful is to write it again in terms of my function h, which is just a helper function to see things clearly. So that is defined as st minus 1 by no, we can here you have one st minus 1, and here you have another st minus 1, so we actually have two st minus 1, and we have minus a square t minus 1 plus a t minus 1. Now again we have to compute the derivative, set to 0 and maximize. So what's the derivative of this function? And plus 1 exactly. And the second derivative, there you go. Yeah, because this goes away, and here you get to the power of 0, so you get just minus 2. Now we can use this again to find the maximum, so the optimal action at t minus 1. It's a little bit tedious, the whole thing. Which, if we take the 1 to the other side, we get this. And then, of course, we can divide by minus 2, and we get that the optimal action at t minus 1 is 1 over 2. Yeah, so that's the optimal action again. So we already now have actually evaluated our, maybe let's write that up, our decision function at t minus 1, which of course takes in as t minus 1. So I'm not writing up the full function definition, just the last bit here. And again, it's a constant function, it's 1/2. It's not the same as the optimal function at the last point, because that was 0. But again, it's independent actually of the value of the state. Which, of course, you can easily, maybe not that easily, but if you would have, for example, if you would have in your, in this function that you're maximizing with respect to, if you had a multiplicative term, so that the st minus 1 times a t minus 1, if you compute the derivative there, then you at least a little bit of the st of the state survive, and then so you easily can also get the state actually as a thing in there. But we don't have that because our functions are not that complex. Now, what is the optimal value function at t minus 1? This we need to find. And this is, of course, well, not of course, but this is the this function, or this function here, if we substitute the optimal action. And that means that we have to put in for at minus 1, we have to put in the optimal action in there at both cases. So this stays 2st minus 1. And then we have minus 1/2 square plus 1/2. And that's, of course, that's 1/4. Also, yeah, 1/4. And this is then 1/2 minus 1/4. So what remains is 1/4. So we have now this and this, and now it's actually 5:30, and I have to stop. And yeah, a nice homework would be to compute this for t minus 2 and t minus 3. You can see that, so the German and the English is not that different. So you can see that in the Schild notes. I can also upload this, then you see that. Yeah. I mean, you could, if you, for example, if, maybe to close this today, if t was in fact 1, and you were only interested in 2 decision epochs, so the 0 decision epoch and the 1 decision epoch, then you would be done now. Then you would know, okay, the optimal action at time 0 is to take 1/2 as an investment, and the optimal action at then the last one is to take 0 as an investment, and you're done.
I have 2 questions.
Yep.
Actually. First one is, here we are changing above, where we put st minus 1 plus at minus 1 is equal to st. But if we put st in the same position, then the derivative is the same.
What?
If we don't put st minus 1 and at minus 1, but rather leave st, then
No, then the derivative is not the same.
like the same as before. It's 2at minus 1, not plus 1, and then it's again 0.
Yeah, but this is exactly the point, that you need to think about what is the transition function. And so the optimization, this is maybe, I mean, it's an important point, but here the optimization, the maximization is done with respect to at minus 1. And you need to think about, depending on at minus 1, how to maximize this. And then you have to think about what actually, how is the state at t plus 1, or in this case at big T, how is that dependent on the action that I take currently? Yeah. So you're thinking essentially one step into the future.
But I would still have at minus 1 in the other position. So
here?
Still, no, that one we leave out and put st. But we still have a dependency on at minus 1.
Yes, but of course so what's happening here, and this is actually, I think, the most crucial thing about the whole thing, is that your current action affects where you get to in the future, and you have to basically take that into account. So this is why you need to take into account your current action. The thing is, this, I mean, the easy answer is, well, Bellman equation says you have to do it like this. And you want to do it differently. That's what I...
But I'm actually not doing it differently. I'm just computing the value of the function at st minus 1 and at minus 1, which is st.
Yeah, but you want to keep this dependent, so this is like 2 plus 1. And if you change the 1, then of course you get a different value for ST. So if you take a different action, so let's say you take as action 3, then you would be in a different state at the next time point. So there's a functional dependence on your current action of what happens in the future.
So I can't just...
No, that's what Bellman Equation says. And this is kind of the law. If you want to see why, then of course you need to look into the proofs of the Bellman Equations. Yeah.
So if we do this up until t equals 0, and S0 is known, then we can go back forward in time and plug in these. So the things that we know when we start applying this algorithm is the structure of the problem and the initial value of S and the time epochs. And that's that.
Yeah, exactly. And as I said, there are also the cases of so they actually, this whole thing that exists in many variations, they also exist for continuous time, where things then turn out to be differential equations, in operations research. It also goes for infinite horizons and so on. So there are a lot of variations. And this is kind of the most simplistic, but then also computational in some way, most demanding case. Okay. Otherwise, I would now stop. And next time, so there is, the thing is with this, so one can do it the way we did now, and we didn't know if t would be 1, then we would be done. What one can show is often, or at least in these simple examples, that there are more explicit solutions, so that you can, by inventing a function that gives you the optimal decision functions, you can then prove by induction that this is a good function. I think I don't want to do that next time, because that would be would take some time, and I would rather show you the probabilistic case, if that is okay. So in the Schild, it says how you can find a general function that solves this. This is what mathematicians are more interested in. They are more interested in, that's all nice that I can do it step by step, but I want to find a general solution that is just a closed form formula that I can apply. And if you can find something like that, is of course nice, because you don't have to run a computer over many time steps and so on. But often, and especially if you're starting out at this, like I'm doing, then running in a computer over a couple of time steps actually works, and then the analytical solution is nice. So I think I will skip that and show you the expected value, where we then again do a little bit of this. Yeah. All right. So then you now can actually apply at Google DeepMind and earn a lot of money. All right. Then see you next week.